really happy that Daan offered to go the extra length to give 2 presentations for the money. so we're very pleased. So very pleased that you agreed to give a second presentation, which is on how we can suppress relaxation.
Yes, exactly. Okay, thank you again for the introduction, and again, welcome everybody. Good afternoon. It's a pleasure to be here, and it's especially a pleasure to talk about this different subject.
The other way around.
Yeah, okay. Don't worry. So here we are. So this is about the relaxation oscillation dynamics. So it's not only the suppression, but it's a little bit beyond that. For semiconductor diode lasers, this optical feedback. Now let me first give an overview of the contents. Apart from the motivation and context, I would like to remind you to refresh a little bit your knowledge about relaxation oscillation. You probably know everything about it, maybe even better than I do, but anyway, so if I say things wrong, then please correct me. But first of all, yeah, you can see here, I call it an instability, so I want to understand the relaxation oscillation instability, and that is of course because of the present background where I'm dealing with engineers who are making and designing lasers that should be used in telecommunication. And they should be absolutely stable, narrow line width, as narrow as possible, you know, and so if suddenly a relaxation oscillation pops up, they call it an instability. It's throw away the sample, it's no worse anymore, it's not interesting to them. But then my interest starts, and that's where they ask for my help. So, so this is about the refreshment of your knowledge about relaxation oscillations. Then I would like to formulate the Lang-Kobayashi rate equations. We've seen them already before. Here, several people are dealing with them, but so I will do it again. And then, of course, I will formulate a steady state solution, and especially I'm interested in the stability of those solutions. And then we'll come in the course of this, as a byproduct, we could give a qualitative insight of how relaxation oscillations might be suppressible. And then I check it by doing an extensive numerical stability analysis, and that confirms, of course, those ideas. And in the context of this numerical stability analysis, I also give you an analysis of the ring. So what happens with the ring in the case that the relaxation oscillations are being suppressed. Then finally I would like to discuss a sort of preliminary result that about the avoiding behavior, as I call it, of the behavior of relaxation oscillations under the influence of slightly small changes of the feedback delay time. And this is very interesting, I think, but this only happens for larger amounts of feedback. Whereas normally in this part of the talk it will be dealing with smaller amounts of feedback, like 1 promille or something like that. But certainly, and this would be almost 1% of feedback, which is already a large amount. Okay, then conclusions, etc. Now, the motivation and the context. The motivation comes from the environment of engineers who are designing lasers that are supposed to be single mode, very single mode actually, side mode suppressions of 40 dB at least, which have very narrow line widths, and narrow line width is less than 1 megahertz, and even much smaller. I will not talk about, but these devices, they are designed by a PhD student. I'll come to her in a moment, but as you can see here, this is a chip. There are 4 lasers on there. Those are the lasers, so those are just optical amplifiers between mirrors. Those are the mirrors here. And then there is an external system, and the external system provides feedback, and feedback is filtered because of the inclusion of a rate waveguide here. And it looks as if all the lasers are coupled now to each other, but that's not the case. They only experience self-coupling. And this arrangement is designed in such a way that that's possible. The AWG here causes the filtering. And the principle is actually indicated here. So we have a Fabry-Perot laser. The modes have a mode spacing of approximately 50 gigahertz. So this is a telecom laser. Then there is an external system, and in the external system there is a part that includes a phase shifter. The phase shifter is also electrically addressable, so that you can control the phase electrically while you are operating the laser. So it means that you have two electrical contacts in the laser. Yes?
So you can address them individually with a phase shifter, or does it?
Yeah, they all have a phase shifter. So those are the 4 phase shifters for each laser. And by accident, this example has 4 lasers, but that's not the point of my talk. 4 lasers. But it is possible to operate 4 lasers, single mode, at slightly different colors, and this AWG also takes care of well, first of all, it will pick out one of those longitudinal modes, and then because also the AWG has a free spectral range, you could also have another mode over there. So you have basically 4 different colors in this device. Yes?
What is AWG?
That's an arrayed waveguide. So
Arrayed
it's an abbreviation. So it's sort of a prism, but then in integrated optics. It's a very nice, very intriguing type of thing. It's a passive element, and there's a lot of interference going on because those are many channels. They all have slightly different optical lengths.
So it's like a bunch of fibers?
Well, it's integrated. So this is
not integrated. I mean, but it's like
waveguides.
Is a lot of waveguides one next to the other.
Yeah.
Is some coupling between them?
It's too small to see here, but those are all parallel waveguides. Well, not parallel, but curved waveguids.
And path length is longer at the outer side.
That's right, and that's why it acts as a prism and also as a filter. And the schematics is indicated here. So we have several 50 gigahertz spaced modes here. We are only interested in one mode. Then we add the feedback. The feedback is very, very weak. It's only 0.1%, but that's already sufficient in order to enhance or to lower the gain of the mode that you would like to start lasing. And because one mode has slightly reduced losses because of feedback here, feedback profile looks like this as a function of frequency. So if you superimpose that here, but remember it's only a very small effect, it's only a very small effect, but it's sufficient to lower the loss of this mode, the preferred mode, such that it will start lasing, and once it starts lasing, it suppresses all the other modes. There's a signal suppression of at least 40 dB. So this works fantastic, and it really makes the laser single mode as desired. But there are some drawbacks, and that has to do with the relaxation oscillations, and that is the part that I would like to talk about. So it turns out that if you want it stable like this, without any relaxation oscillation, you really have to carefully adjust the phase that you add externally. But if you then change the current a little bit, then you lose the stability again. And okay, we'll talk about that. This has been described in those papers. So this is all work by a PhD student, Jing Zhao, and she just got a PhD early this month. Okay, those are the crucial results that I would like to show you. So this is a case where the laser is operating far above threshold, approximately a firm strength of 3, so 3 times above threshold. And they are all taken at the same operation point, except that the phase has been changed a little bit. So, just electrically. And then you see for one situation, it is difficult to say how big the phase exactly is. It's not so relevant. What is relevant is that this has a different phase from that one, etc. So those are 3 different phases, varying between 0 and pi. Yeah, because it was difficult to get 2 pi all the way, but pi was easily doable. So this is already what you see in an interval of phases from 0 to pi. So this is stable, this is very single mode. as you would like to have. Yes.
So just to understand, so what was done in this plot is the current was increased until you had, for no phase shift, a single mode operation, and then you scanned the phase.
That's right. So you carefully adjust the current until you find a situation like this. This happens to be a situation where the relaxation oscillation is given by this quantity, 6.8 gigahertz, very normal value, and this also is pump strength. Of course, yeah, this was a pump strength of about P equals 3, something like that. So 3 times above threshold. The threshold of this laser was 12 milliamps, no, 16 milliamps, so we are dealing with approximately 60 milliamps or something like that in that region. So the only thing that is changed is the phase here. Now here we have a stable mode, and if you look at the rim, we see the usual thing, you know, a relaxation oscillation structure, which is around here, but it's very quiet. The rim is very quiet, and there's nothing special going on. The line is very narrow, and actually a measurement has been done which gave 120 kilohertz for the line width of this line, which is completely according to theory for a laser with feedback. So nothing special concerning that. It's very nice. It's a very nice technological result. But the bad thing is that if you lose the control of the phase, then things like this happen, and which we find, of course, very, very interesting. So this is just this is dynamics. We can find this is the signature of dynamics in the rim, and it occurs exactly at the 6.8 gigahertz. So this is the relaxation oscillation. We can see it here in the optical spectrum, and we see equidistant peaks separated by the relaxation oscillation frequency. So this behaves very nice, it's well understood, and somehow there has been a hot bifurcation going from here to there in between. Now then there is another bifurcation, a period doubling bifurcation. If you change again the phase a little bit, as you can see here, we see the original relaxation oscillation peak, but now there is a new peak at half the frequency, so the period has doubled. And here we see the optical spectrum, where we have twice as many relaxation peaks as before. Now, then we can go to yet another value of the phase. As we can see here, still the relaxation oscillation is dominantly present. Also the period doubled one, but there is but the overall noise level has increased a lot here, and you can also see it in the optical spectrum that there is now, it is partly a continuous spectrum now. And so that would be a strong indicator of the fact that you are approaching chaos here. And okay, but this is all what the engineers don't like. They throw away samples like this, and they can't use it. So the question is, the conclusion already from this is that stable single frequency operation really depends crucial on the feedback phase. Now that's not something you like. You don't like to have to control the feedback phase electrically. And besides that, once you have found it and you change the currents a little bit, you are away from this point again, and you lose it again. And then you have to, again, very carefully adjust the feedback phase. You don't like to do that. That's not a practical device, you know. So I think it is correct for them to throw the samples away. But then the question immediately, and that was my question, can we design the laser now in such in the same spirit? Can we design it such that the stability is maintained independent of what the precise phase is? Because then we don't need to include the phase section on the chip and do it without that, which makes it much more simple. Technologically, it is much better accessible, and the stability, of course, is much better. So that is the question. That was the question that I wanted to answer. Okay, now before we can do that, it is good to understand a little bit the relaxation, oscillation instability, as I call it. I mean, maybe we shouldn't call it instability. And actually, I discussed it with Wolfgang Elsesser already. Well, it was about a year ago, and he didn't like the word instability. So that was, in his opinion, not good to use it like that, because the instability, or it's just a property, intrinsic property of the laser, and you shouldn't call it an instability. But anyway, okay, this is just engineering talk. So what is a relaxation oscillation? It can become undamped. We've seen that. We've seen the spectra. And then there was a theory. This was quite popular to study these things in the late 80s already. And there was this Danish group of Merck, Tromborg and Mark, and they had this theoretical analysis, but they did it for one particular feedback phase. Normally you take 0 because that's the easiest case.
And also that is a long cavity.
Sorry?
In the Mork and Tromborg paper, it must be a long cavity in that case. Yeah? They want the short cavity.
No, it's not that long. So the long cavities are here. No, let's see. The long cavity means no. This is the long cavity side, and those are the short cavities. Because what is horizontally is the relaxation oscillation frequency multiplied by the external delay time. See, and if there is a resonance in that sense, there are several resonances. The laser is more stable here because this is the Hopf bifurcation line that occurs, and the pump strength of the laser is of course hidden in the relaxation oscillation frequency here. So this already uses a sort of scaling property of the relaxation oscillation and the external cavity length here. So this according to them, this is the relevant quantity to consider. But it's very interesting because for very short cavities it's always stable, but this is in practice this is an infinitesimally small region, so you hardly see it. But those should be visible, and we actually saw them because the existence of this region is the reason that we were lucky with the other laser that there was a stable region. But when you change the phase, well, this has no information about phase, of course, so we cannot consider it yet. But it would be nice if, for instance, those tongues here, those tongues of stability, would be independent of the phase, or would survive if you take the phase into account. Because then you have the possibility of at least a band of pump strengths where the laser becomes stable, independent of the phase. So that's the idea, but then we need to know what happens if we change the phase. So that is the central question. What about other phases? Because this was taken at one particular phase. And they overlooked, at that time, they admitted that, they overlooked that it might be interesting to go to other phases as well.
More actually very early experimental works already in the 70s, which looked at the interest.
70s is very brilliant. I'm not aware of that. But I know that in the 80s, in the 90s, there was something that, well anyway, so, well, yeah, it's too late to use them for me. But I'll be interested to see them, yeah. Right. Okay, now, so in any case you predict higher stability at feedback delay resonances, that's the point. So that's the hope now, that we could design a laser in such a way that you're always somewhere in such a tongue, and that it will indeed be independent of, or to some extent independent of the phases. But that remains to be seen. But then, how do you understand this? Because there was not even a qualitative story given why this would behave like this. So I would like to understand it in my way, and I will show you how you could qualitatively understand it. Now the clue is, I'm already telling you, is in the delay equation. So once you have formulated the delay equation and you have looked at the small signal equations, then it is almost trivial and obvious, but we'll do that later. So, okay, now just as a reminder, what about relaxation oscillation? It is like Wolfgang Elsasser said, it's a damped natural eigenfrequency of the coupled carrier and photon system, so it's just intrinsic to the solitary laser. But for a solitaire, it's a damped oscillation. You only see it when you have a transient response. So that's the only way to see it. But also indirectly, you can see it as a peak in the ring spectrum, as everybody knows. So this is actually drawn in a letter that Wolfgang sent me. It's his picture. So I thought it's nice to put it here. Okay. So now, how can we understand all this? Very simple. We go to just a single mode equation, which is this one without feedback. This is the solitary laser. So this is the power. This is the inversion. Those are the only relevant quantities because the phase is just following them. Okay, steady state is given by this, so it's proportional, the power is proportional to the pump strength as indicated here, and the carriers are clamped. But then you should look at small perturbations, because that is then you only can see them by perturbing the laser. We take small perturbations, and then it's easy to derive from those equations and doing a second derivative with respect to time to derive this equation for the small deviations of the inversion. And we recognize this, of course, as a damped harmonic oscillator. This is the damping which involves, apart from the lifetime of the carriers, also the photons in the laser. And this is the square of the frequency of the oscillation. So, the relaxation oscillation frequency, then, if you analyze it precisely, is given by this quantity, square root of this here, the pump strength basically, minus a small correction which is associated with the damping. You recognize a similar term as, or the same term as sitting here. So the damping is given by this quantity, and the frequency is given by this. Now, since most of the time this is a negligible quantity with respect to this pump strength term, the relaxation oscillation behaves as the square of the pump strength. But very close to threshold, and this is also very small. You have to be careful, because this will become negative at some point, and then it will be there will be no oscillation anymore. It's critically damped oscillator there in that regime. So it is interesting, but it's not part of the present talk. Okay, this is an example of how it could look like.
Do you know? Yes? Do you know whether this has ever been used to determine capital T, so the electron lifetime?
Ah, you mean, okay, you go the other way. You want to use this in I have no idea. I suppose. So but psi P is already concerned from. Yeah.
Sure, but you still would need to know it.
It's an interesting idea, but yeah. You really have to be an experimentalist for such ideas. Yeah. Okay. Well, anyway, so let's continue then. Okay, so now I would like to formulate the equations describing the laser with feedback. So, and they are the famous Lang-Kobayashi equations, as you all know. They were put forward in 1981, if I remember correctly. In any case, a long time ago. So, but they seem to be very adequate, and they still are very adequate. They are widely used, and so I repeat them here. For the inversion, there's nothing new. It's just the same equation as for the solitary laser. The feedback is explicitly present in the power and in the phase. The first terms are the same terms that you have in the solitary laser, but the feedback is present in those terms. It looks a little complicated because I took the real and imaginary part of everything, because I describe it in terms of power and phase, but it is like this. So it can easily be analyzed for the steady state solution. So now we look for solutions for which P dot is 0, N dot is 0, and phi dot is not 0, but phi is then just a fixed frequency times T, and this fixed frequency is the feedback induced frequency shift. And that's how we interpret it. So that's what I call the steady state solution. Then the power is given by this expression, so it involves the current. It involves also the new feedback induced value of the carrier number, as indicated here, and the carrier number is given by this expression, just proportional to the feedback rate and the cosine factor here. And in this cosine we have already the feedback phase, as I call it, because omega naught is the solitary laser frequency. So this is the intrinsic frequency of the mode, you could say. Then there is a shift because of the feedback, it's called delta omega. Delta omega has to be solved from this equation here, so this is a transcendental equation which for delta omega s, the frequency shift, can be solved numerically, or you could and then once you know that, and you know the phase, because this is the phase, this I consider also, I identify this as the feedback phase of not store, and this one can be manipulated with the phase element. So if you put a phase element in it, you add another phase here to it. Okay, so this can be solved, but then of course this is not so interesting by itself, because we know that there might be instabilities, and so this may not be representing the stable solution. So we have to do, investigate the stability of this solution, and we do that by looking at small deviations from the phase that it would have if it was stable. So we have a delta phi, which is supposed to be small. Then we have a small excursion from the steady state power given by delta p of t, and the same for the inversion, like this. And then we can formulate, we can derive from the original equations, we can derive equations for the small deviations, which is given by this. One for the phase, one for the power, and one for the inversion. And now you should look carefully what's going on here, because this one is driven by the phase excursion on one round trip. See, and the same is true here for the power on one round trip. Here again it's the phase on one round trip. This one is the plus sign, so here it adds, so that this is a different term. But those terms are important, because if there is a relaxation oscillation, suppose the laser, for some reason that we don't understand yet, but for some reason the laser will experience relaxation oscillations. Now, and if you tune the external cavity length in such a way that it really corresponds to a period of the relaxation oscillation, this term is the zero, it vanishes. It cannot do anything. And the same for this term, the same for that term. So let's look how and that's a small excursion that I will do here. Let us assume that the relaxation oscillation is at a resonance of the delay time, like this. So it's 1 or 2, the product of the 2 is 1 or 2, etc. Then these quantities will be equal, those will be equal, and then the equations reduce to those equations. And those equations are in fact exactly the same equations as you would have for a solitary laser. And a solitary laser, we know the relaxation oscillations are then. So there are no relaxation oscillations in the solitary laser. So under the resonance conditions for the relaxation oscillation, the system will behave as a solitary laser. It will not show any relaxation oscillation. Now, this is not correct under all circumstances, but it is certainly correct for not too big rates of feedback. So, and that I will show you later with a real numerical analysis. But this is the qualitative argument why the relaxation oscillation will not show up if you tune the laser such that the relaxation oscillation is resonant with the external cavity. Yes?
And the external cavity should be shorter, cannot be shorter than the relaxation time.
That's right, that's right. So it should not be too short. So when you are dealing with integrated lasers, you have already one technical problem. And that is that in an integrated laser, it is difficult to make an extended external cavity. So 1 millimeter or 2 millimeter is doable easily, but if you want to go, and you want to go here to, say, 10 centimeters external way, you have to sort of spiral the waveguides in order to get on a small area to get this long delay time. It is possible. It can be done. Yes?
Just understand correctly this resonance condition that you define, because it includes that the delay phase also vanishes, right? So
that's right. That's right.
It's even a stricter condition than just having the relaxation oscillation being resonant, because that means also the phase at the same, even on a phase level, it needs to correspond. Right?
Yeah, that's right. That's right. That's right. So if you have noise, other noise, etc., it could be distortion. And in practice, we will see that it's only the first and the second resonance seems to work. If you go, if you go to higher resonances, So then it doesn't work anymore. And also if you add too much feedback, then you get other effects which are also very interesting, but then it doesn't work either. So, but anyway, so this gives hope that you could find a regime which is technologically accessible where you can suppress the relaxation oscillation in this way. Okay, so let's now do the stability analysis. So what I'm doing now is just continue here and find solutions for find solutions for those equations, and I do that by just doing a Laplace transform in standard way. So that is being done here. So I look at those solutions for complex S. Then there is a determinate equation is given like this, and we have to solve this for S in order to find the solution of those equations. And the ds function is a complicated function in terms of all the laser parameters, as indicated here. So it is a bit of work you have to do. But in any case, if you have a solution of this equation, then the only thing, and you look for solutions in the complex S-plane, if the real part is smaller than 0, then the steady state could be stable. And that should be valid for all solutions of this equation. And each steady state solution of the laser gives rise to one expression as indicated here, because this contains all the parameters of the steady state laser. As you can see here, the delta omega S, BS, they have already been calculated. So, and then you have to solve this, look for all the poles, and there is one way, a very elegant way to find numerically a criterion that all the poles have a real negative part, and that is the principle of the argument. So that has been employed. I will spare you the details, but you can do that. And it's very easy to put that in a numerical procedure. Now that leads, if you do that, that leads to a stability diagram for a laser with delayed feedback. And this gives such a stability diagram. So this was a laser with 1 promille of feedback. So that means that my gamma is 10 to the 9th. The feedback delay time is 300 picoseconds, which corresponds, I think, to 12 centimeters or something like that. The C parameter, which is the product of gamma and tau times square root of 1 plus alpha squared, is smaller than 1, which is nice, because it means that there are no new external cavity modes. So there's only a perturbed original solitary laser mode. Nevertheless, it's not always stable. The unstable regions are the black regions here, as you can see. There is, okay, but something has been left out in this analysis, and that's the fact that it's well known. Now, first let me explain what's standing here. So here, vertically is the pump strength of the laser, so this is basically the current through the laser starting with 0. This is the threshold here, and this is the phase that is added here, and that is taken into account, and this can be seen as the electrically accessible phase. Then I have also indicated the corresponding relaxation oscillation frequency for this particular laser, which varies also from 0 somewhere here close to threshold to a value of 6.6 here at the pump strength of 3, 7.7 there. And I have also indicated the product of the relaxation oscillation frequency and the delay time, which is, and that would give you a number 1 here, 1.5 there, 2 there, etc. And it doesn't surprise us that there are indeed now 2 stable bands, one corresponding to the first resonance and one corresponding to the second resonance. And they are indeed stable for all values of the phase. But what I left out here is the fact that if you crank up the current here, that you induce also a huge phase shift and a huge external phase shift, because the frequency of the solitary laser is changing. And that can be a lot. For instance, like -1 gigahertz per milliamp. And that is because of, I think, the dominant effect is the heating of the laser. That will make the modes to start running. And Okay, so that means if you multiply this frequency shift with the feedback delay time, you get a feedback delay induced phase shift that can be as much as -2 radians per milliamps. So you are really going through this picture. And the picture then actually looks completely different. People were, okay, this is to show you that this is for one particular laser. You can see that it's not always nicely single mode, so it could also happen that other modes come into play. But this one, at least, is here. So it starts off single mode, but it's not such a good example. But what you can see here is the feedback, the current-induced redshift of the mode frequency. Yeah?
But this is without feedback? Or
This is without feedback. It's just solitary laser. Yeah. Now, yeah, is it without feedback? That's a good question. I don't know actually. I don't know when it's without feedback. But in any case, so it's just a measured spectrum in the output, and then as a function of the injection current. But anyway, so what she measures is 0.6 gigahertz per milliamp. It seems to be a good value. So that is the tilting of those vertical lines. It's given this quantity. Okay, now let's plug that in. If I plug that into my picture, which was just a simple, band structure thing, now it becomes a complicated band structure thing. So the whole instability region has now deformed in lines, like this. And so if you have a certain phase and you just crank up the current, then very complicated things can happen. This is unstable, then you have stability, it's stable again, it's unstable, here it is stable again, here it is unstable, etc. So the black is unstable and the other is stable. So this is how it will present itself to you if you do the measurement. And you should consider yourself very lucky if you find, suppose you have not taken into account this condition, to find a stable region. And you should not be surprised that you lose stability very easily. So now this was more or less measured and was qualitatively in good agreement, but the details were a little different. So it was, I did this, I just guessed many of the parameters, but at least qualitatively there is agreement with, apart from those bands, because we haven't seen that experimentally yet, because it is a different conditions than the laser that she designed. So she designed a laser where this is not present. And adapted such that you have this region. And then I would propose, now this is more than 10 milliamps, this is several, maybe 15 milliamps or so. And that would be very nice, because that's not so difficult. Even if you don't have a lot of accuracy to operate the laser there. Yes?
Wouldn't this stable, if you have construct such a laser, would the line still remain phase independent?
That's a very good question. The answer is, I can tell you already now, it is not. It is not. So the line width will still be very much depending on the phase. And so you still need phase element if you really want to tune the laser at the narrowest line width. But that is at least what the theory is predicting. So you're right. So that is, but at least it is stable. It is stable. And the line width, because the line width narrowing factor heavily depends on the phase, on the feedback phase, as you know. So you could get, it goes with 1/1 plus C times, and C contains also the alpha parameter, times the sinus of the angle, or something like that. So you could get narrowing factors of as much as 5, but also it could broaden. But it does not get unstable. So that is the good thing about it. Okay, so let's see. Oh yeah, now this is a sort of corollary about the RIN. The RIN, of course, I assume now that I'm considering a steady state, because this is all based on small signal analysis. So I consider a steady state, and in the steady state, this is the expression for the RIN, where you recognize, well, those are just laser parameters, and this is the same function that we have seen before, that also plays a role in stability analysis. So this can easily be calculated, and that gives us, but only for steady states where I know the exact oscillations. Otherwise it's not valid. But we could still do it then, but we find things that you don't know what it means. So if I do that, I do it in this situation. So I take a simple case, this one, with the original picture, and I take position here along this line, and I want to know how does the RIN change when I move here from below the gap to above the gap. And the points A and B mark the precise transitions here. So those should be Hopf bifurcations, and that's at least what we believe. Because here there is no relaxation oscillation, then the relaxation oscillation pops up, causes this instability, so this should be a Hopf bifurcation, and it should be there. It was actually Wolfgang, again, who raised that question. And then I realized I didn't know the answer at that time, but I realized I can easily calculate it, so that's why I did it for this particular situation. So, but this only valid within the gap, because that's where the steady state exists. Here it's not valid in a different analysis. Okay, now those are the results. First of all, I show you here what comes out for the solitary laser, which is here, for a pump strength of Xi, which is in the middle of the gap. The gap indicates this feedback. Then it looks like this. It looks very normal. There's just a peak at the relaxation oscillation frequency, etc. Nothing special. But sharp peak at the relaxation oscillation frequency. How can you see that? Because this is exactly 2 pi. Exactly 2 pi, and the external cavity frequency is actually seen. You can see it already here, sitting here. So it gives a structure in the ring. And so that is. So this is. This is 4 pi. This point. So it's about 12, something like that. And 2 pi is sitting over here. So that would be the external cavity frequency. Yeah. Okay, but what is noticeable is that there is this very sharp peak. In this case, you see the external cavity frequency here, very visible. And now if we go further, we go above and we approach the end of the stability region, then again a very narrow peak pops up, which is a sort of precursor of the dynamics that will occur, the relaxation oscillation dynamics. But I cannot go further because if there is dynamics, the theory is not valid anymore. So, but in any case, I think this very nicely illustrates what happens in the RIN when you are close to that Hopf bifurcation, creating the relaxation oscillation. Okay, now this is finally, and then I'm done. So that'll be the end. This is something I would like to share with you because I found this very interesting. And I call this avoiding behavior of the relaxation oscillation frequency under strong feedback conditions. So this is different from what I talked about before, because the feedback now is really larger. It's 0.5% in this particular example, and the C factor is bigger than 1, so we have more than 1 external cavity node involved here. But the idea was that we would like to see, this is a calculated optical, a simulated optical spectrum, which has a relaxation oscillation. Well, you can just measure it in the spectrum. It's 4.9 gigahertz, whereas the solitary laser would have a relaxation oscillation of 5.42 gigahertz. So we see already strong feedback-induced deviations for the relaxation oscillation. Okay. Okay, nevertheless you could, and you can calculate the product of the relaxation oscillation frequency and the delay time. It's all 1.84 here. So you should compare this frequency with twice the external cavity frequency, which is this one. Now, so you think, okay, let's change the length of the external cavity a little bit so that this factor becomes closer to 2, because then the relaxation oscillation might be disappearing. At least that's what you hope. The answer is it won't, and that's because we have too much feedback. So what happens actually if we do that, we come in this situation. So in this situation, the relaxation oscillation frequency is still very close. Well, one of it, there is actually a bar-stable case. There are 2 relaxation oscillations now, and we changed only the external cavity length a tiny little bit, so that this frequency is almost the same as there, but if the relaxation oscillation stays like this, we get closer to the factor 2. So indeed, this is 1.85. But the other relaxation oscillation, and they are approximately equally likely to occur, gives us a factor above 2. So somehow, when you thought, okay, this is the situation that we are aiming for, and it is 2, and the relaxation oscillation should disappear, the relaxation doesn't want to die, it wants to survive, and it survives by just choosing different values like this, and it avoids this point. So the intersection, it's a sort of avoided crossing, and the crossing avoids that they become equal. If you go a little further, I think I lost my battery. Anyway, if you go a little further, we get the picture in the upper right part, and then we are beyond the factor 2, the product of 2, and the relaxation oscillation is 5.7 there. The funny thing is that the average of the 2 relaxation oscillations in the lower curve is more or less the solitary laser relaxation oscillation. So what you can see already, but I did not work that out, but that was the idea that Wolfgang Elsass, I think Wolfgang had, but I haven't corresponded this with him yet. But I think that is what he had in mind, and avoided something with a branch that would go like this, another branch that would go like that, then a jump, then another branch that would go like this. It seems that this is what we had in mind. So this is all numerical. And so the whole idea of suppressing the relaxation oscillation doesn't work anymore if the feedback is too big. That's the message. Okay, so the whole thing doesn't work anymore. I'm sorry, I run out of battery. Okay, so the conclusion is that narrow line with single mode integrated laser with delayed feedback is hampered by undamped relaxation oscillations, and that whole process is very sensitive to the precise phase in the laser. And then under resonant delay and weak feedback conditions, so that's very important, so resonant delay and weak feedback, the feedback suppresses the relaxation oscillation. And that has been shown theoretically. It has not been demonstrated experimentally, which is surprising, but it seems to be, simple thing, but it's not so simple, it seems. So I don't know. I haven't seen an experimental demonstration yet. So if you have a laser lying somewhere here, and you could do it easily, then I would be very happy, of course. It's possible. But anyway, if I'm correct, this would imply the existence of injection current windows where the operation is stable and it has sizable width in terms of the pump strength of the pump current, 10 milliamps. So that is feasible, and then it would be independent of the stability, is independent of the feedback phase, but like Ingo already remarked, the line width narrowing is heavily dependent on the feedback phase. So there might still be interesting things to be discovered. I haven't done that yet. But it all needs to be confirmed by experiment, and if it works, it could form, now I'm sure it will form the basis for new designs of lasers, integrated lasers. So thank you very much.
Thank you very much, Dan. Questions?
You said that for initial product of relaxation oscillation in daytime, the small signal responses of the laser, of the late count laser, breaks well down to the solitary laser then.
Yes.
The small signal response. Can you?
Yeah, I can show you. It was the qualitative argument.
Yeah.
So here, that's this one. One before. So this is Lang-Kobayashi equation.
Yeah, the next one.
It's the steady state.
Yeah, this one.
This one?
No.
This one?
And the one after is the definition.
So,
This one.
exactly, but if you now go to the one before,
Yeah. So you just.
so you have the delta phi due to the feedback, no? The phase change feedback in these equations.
Yeah.
Do you have where do you have the random phase you can also put in by the phase control in this equation?
The phase, well, you mean the electrical phase control?
Exactly.
That is in the omega naught. The omega naught. So the omega naught should, and the omega naught times tau, then has a correction in the decay.
Right.
Because of the electrical phase that you add to the laser. So that's easily taken into account. It's not really important.
Because I understand the mechanism why maybe the relaxation oscillations disappear if you have exactly an integer value of 2 pi phase shift between the delay field.
Yeah.
That this also disappears for whatever random phase shift is?
That's, because the phase shift means that you have a certain setting of the laser. So, and that is being taken into account. So first you define your laser parameters, including that electrical phase shift. Then you find the solution for the steady state values, including the delta omega s, which you have to calculate them, and then later on you plug that into these equations. So, it's not too difficult, but you have to do a little bookkeeping or something like that. And it's very consistent.
Let me ask you as theoretician, nevertheless a practical question.
Yes.
What is the original intention of the laser design that you showed? Are those lasers for EWDM or for WDM?
Okay. That's good. Let's see. Let me just show you a picture. They were designed for. That was for the. This was for. Okay. That's not my work, but they were. It was a project where astrophysical data from electrical data. They had to be. They had to be handled, and the handling, the communication of those electrical gigahertz electrical data was done optically by using fibers, etc., and then using those lasers. So there was also the ultimate lasers were more than this, because they also had a modulation section. So it is a little bit bigger, and it has a modulation section to the left.
Radio or fiber?
It's not really, no, it is not radio fiber. So that's, you're asking things that I don't really know. But if you're interested in, I could get you a copy.
I would be interested, because I was wondering, in case of the stability, what would one gain, for example, if one gets certain stability of the laser, if one could keep the frequency constant, one could define nicely, for example, frequency channels. But I guess that with the phase section tuning, one still might get also a variation in the wavelength.
No, that's not. I don't think so. So they were actually operating properly, even with the modulation extension, and it worked. and very surprisingly, in the 4 colors, so they all work together, yeah, and there was no crosstalk, or not a lot of crosstalk. Of course, there's always some crosstalk. It's not a lot of crosstalk, so it really worked.
Did you ever discuss with Smith to adjust or to design the AWG such that it couples the lasers?
I think they have done that. Okay, but I still don't really understand the AWG. I think it's an awfully intriguing element, and it is relatively simple to make it, to fabricate it like this, and to integrate it. But yeah, I don't know. So I have no real control over an AWG because it's so complicated. If you try to describe it theoretically.
I have a very naive question. I think that the second picture you have there, the one in the bottom, is just a sketch of what is really
yeah, sure.
But I can imagine that the feedback comes from the reflectivity or the change of refractive index between the device, the feedback section of the one section and the other.
Yeah.
Couldn't you tilt a little that facet to avoid or to reduce at least when you cut it? You go perpendicular.
She measured all the spurious reflections because there are reflections everywhere. Here, for instance, there are reflections here, there are reflections here, unwanted reflections also, and they are all visible in a certain technique, and you can see them precisely where they come from. But they were all
many of them
small enough that they didn't bother the operation of the laser. So they were under control. Yeah, it's. I was in the beginning. I was extremely surprised that it really worked like this. It seems it works. And the techniques, the fabrication techniques are highly reproducible these days. It's fantastic. Yeah. So.
Further questions? If that's not the case, let's thank Daan again. Thanks a lot for.
So timing was better.
Yeah.
It's very interesting. Yeah, there's this regions, the resonant regions where the voice is.
Yeah.
Because I was thinking at the beginning, I would also say, okay, just